This video will cover section 2.5, zeros of polynomial functions, and this will be part 1. So we're going to start by looking at a polynomial in factor form. And remember how every time you have a factor, we know that we can equal that to 0, and then to solve for, when we solve for x, that will give us the number where the 0 is actually happening. If that number is real, that means that that is actually an x-intercept, a point on the x-axis. So the 0 that comes from the first factor is x is equal to -3. The second factor, if we take 2x minus 1 equal to 0 and then solve for x, we will get 2x is equal to +1, and then we divide by 2. So the second 0 will be x is equal to 1/2. The third 0 is going to be x is equal to the negative square root of 2. The fourth one will be x is equal to the positive square root of 2. And the second to last will be x is equal to +4 minus 5i. And the very last one will be x is equal to +4 plus 5i. So what we're going to do next is classify the zeros. And so we know that the first 4 of them are real numbers. And the last 2 are imaginary numbers. Now, we're going to get a little more specific, and we're going to say that the first 2 are rational numbers. Now, remember, rational numbers are a subset of real numbers. And these are numbers that could be written as a fraction, or they're actually defined as a ratio of 2 integers. If we look at the square root of 2 and the negative square root of 2, those are irrational numbers. Some examples of irrational numbers could be pi or e, or any square root that does not have an exact solution. So but keep that in mind, both of those, rational or irrational, they're both real. The imaginary numbers, imaginary zeros actually, are the ones that will contain I. So that will take us to the first one of the theorems for this section, and that will be the rational zero theorem. So first, I want you to write the following definition. If f of x, and we have the polynomial here, remember n is the degree, and a sub n is the leading coefficient. So if we have that polynomial, and the polynomial has integer coefficients, and we're going to use the letters p and q just to represent numbers, more specifically integers. Remember, a rational number is the ratio of 2 integers. So if p over q is a rational 0 of f, then we have that p, remember that is an integer, is a factor of the constant term. And that is represented by a sub 0. This one, that is a constant term. Also, we have that q is going to be, so it's a factor of the leading coefficient. And remember that one is represented by a sub n, the one here. So what we're going to do with this theorem is that we're going to look at the factors of the constant term. We're going to look at the factors of the leading coefficient, and then we're going to make combinations, and that will tell us the possible rational zeros. So don't forget, we're talking about the factors of the constant term. Divided by the factors of the leading coefficient. So now let's go ahead and apply the rational zero theorem. And what we're going to do here is we're only going to list all possible rational zeros. It doesn't say to solve the polynomial or to find the zeros, only to list all the possibilities. So what we need to do, let's define first, what is the constant term? Constant term is represented by a sub 0, and so that is equal to 4. Now, a sub n is the leading coefficient, and that one is represented not by 1, but actually by -1. So what I'm going to do is list all the factors of 4 and divide them by all the factors of -1. So the factors of 4, we have 1, we also have 2, and we also have 4. But now we could also consider -1, because 4 could be divided evenly by -1, also -2, and also -4. So the way we're going to shorten this is going to be by using the plus minus sign, or a combination of a positive and a negative. And that way we're implying that we have +1 and -1, a +2, a -2, +4, -4. So if we divide this, and we're going to divide them by -1, factors of -1 will be also positive and -1. So now this problem is kind of easy, because once we list all the possibilities, so here we're only talking about possibilities, and that will be the possible rational zeros. So those will be all of these numbers. So let's say positive and -1 divided by positive and -1. So that will be positive and -1. The next one will be positive and -2 divided by positive and -1. So that will be positive -2. And also we will have positive and -4 divided by positive and -1. So in here we have only possibilities. Remember, the degree of this polynomial is 4. That is the highest exponent. And so we know that we could have at most 4 zeros. So how many possibilities do we have here? If we consider the positive ones and the negative ones, we have a total of 6 possibilities. And that's it. That's all we have to do for this problem, because we were only asked to list the possible rational zeros. Now let's go to the next slide. Now what we're going to do with example 2 is the same thing, but now if you notice, the leading coefficient is 15. But let's first establish what the constant term is, that is represented by a sub 0, and that is -2. We also have a leading coefficient, and that would be 15. Now we're going to apply the rational zero theorem, so that means that we need to list the factors of the constant term, so the factors of -2, and divide them by the factors of the leading coefficient, which is 15. Now the factors of -2 are just going to be positive and negative 1, positive and negative 2. But the factors of 15 are going to be positive negative 1, positive negative 3, and positive negative 5. Oh, and I'm missing 2, positive negative 15. So now when we list all of our possibilities, this will be the possible rational zeros. They're going to be all of this 4 numbers, and I say 4 numbers because we have positive 1, negative 1, positive 2, and negative 2. So those 4 numbers are going to get divided by positive negative 1. So that will be positive negative 1, positive negative 2. The next one will be the same 4 numbers, but now divided by positive negative 3. So that is going to give us some fractions. But remember, if we're talking about rational numbers, they could be integers or they could be fractions. In fact, integers are also fractions. It's just it happens that the denominator is equal to 1. So in this case, we will have positive negative 1 divided by 3. So that will be 1/3. And we will have positive and negative 2/3. And then we take the same numbers, and now we divide them by 5. So in this case, we will have positive negative 1/5, and also positive and negative 2/5. Now we have the same numbers, and we're going to divide them by 15. So this will be positive negative 1/15 and positive negative 2/15. And that's it for this problem because we were only asked to list the possibilities. So how many possibilities do we have here? We have 2, 4, 6, 8, 10, 12, 14, and 16. So we have 16 different possibilities. Remember, we're considering the positive and the negative combinations. Now, we know the degree of this polynomial is of 3, so we could only have at most 3. Now, that doesn't mean that all of those are rational. Some of those could be irrational, and others could also be imaginary, like we had on the first slide on this polynomial. So let's go back to second slide, example 3 now. And so now we're actually asked to find all zeros of f of x. So for us to do that, you might be thinking, well, maybe I could factor it. It is a polynomial that has 4 different terms, 1, 2, 3, 4. So we could try to factor this one by grouping. Maybe we could group this one with 2x squared, and then negative 5x minus 6. And here, if we were to take a factor in common, it will be x squared. We will get something like x plus 2. On the next one, there's nothing in common. Maybe we could take out a negative 1, but then we will get 5x minus 6. Now, you might be thinking, well, what if I switch the order of the terms? So if we do that, let's say we group x cubed with 5x. And then we group 2x squared minus 6. So even if we do that, you could see that we will not be able to factor it by grouping. The reason for that is that the factor that comes here is not the same. So for that reason, we are not able to factor it by grouping. So we'll have to rely on other methods, and that method will be to use the rational zero theorem. So we're going to use the rational zero theorem, and we know that we must list all the factors of the constant term, which is -6, and we're going to divide those by the factors of the leading coefficient, which in this case is 1. We don't see a number, so there is a 1 there. So what we're going to do now is list the factors: positive -1, positive -2, positive -3, and positive -6. Here, we're only going to be dividing by positive -1. So now to list the possible rational zeros, we're going to use those numbers divided by positive and -1. So we will have positive -1, positive -2, positive -3, and positive -6. Now, here, how many combinations do we have? Or possibilities, I should say. So if we consider 2, 4, 6, and 8, because remember, we have positive 1, -1, positive 2, -2, positive 3, -3, positive 6, and -6. So we have 8 different possibilities. Now, you have to keep in mind that this theorem was created when graphing calculators were not existent. So, but now we have them, and so we're going to make good use of them. So what we're going to do now is, with your graphing calculator, I would like for you to graph the polynomial. And so the polynomial is x to the third power plus 2x squared minus 5x minus 6. I'm just going to move the equation here. And so we can see here that clearly, since the window is set to go on a scale of 1, we have here 1, 2, and if we go on the negative side, on the left side of the y-axis, we will have -1 and -3. So we're going to make wise choices when we check for our rational zeros. So our choices here, or educated guesses, are going to be -3, -1, and +2. And we know that because we see the function crossing the x-axis. So from here, we're going to take -3, -1, and +2. So we're guessing, remember, this is an educated guess, that our zeros are x equals -3, x is equal to -1, and x is equal to 2. However, for this class, you are required to prove that those are in fact the zeros. Graphing it on the graphing calculator is not going to be enough. So what you will do is use synthetic division. And remember that by the remainder theorem, if the remainder happens to be a 0, that means that that number is in fact one of the roots of the equation, or a 0. So in this case, we use -3 for the first one. And we need the coefficients. We have to make sure that they are in descending order, starting with the greatest power, and that we're not missing any of them. So we have x cubed, x squared, x to the first, and remember the constant term is x to the 0. So we can list the coefficients: 1, 2, -5, and -6. Now we're going to perform synthetic division. So the first step is to drop the first number, and then we multiply -3 times 1, so that is -3. And then we combine like terms, so 2 minus 3 is equal to -1. Then we multiply again, -3 times -1, and that is +3. If we combine like terms, -5 plus 3, that is -2. Now we multiply -3 times -2, and that gives me +6. And if I combine like terms, I can see that in fact the remainder will be 0. So what that means is that I have verified my first guess, and that is true. Now what I can do now is to keep doing synthetic division, but what I could do is use the new coefficients and not go back to the originals, because the remainder was 0. I was asked in my other class if the remainder wasn't 0, if we could do that, and the answer was no. If the remainder happens to be other number than 0, then you will have to go back to the original coefficients, the ones there. But that is not the case. So now we could keep doing synthetic division here, and the next number to test for is -1. So we drop the first number, that is a 1, and we multiply -1 times 1, that is -1. Combine like terms, -1 minus 1 is -2, and then we multiply -1 times -2, and that is +2. If we combine like terms here, -2 plus 2, that is equal to 0. Now here we could do synthetic division again with +2, or we could use something else. Let me show you. So we started with a polynomial of degree 3. This was the coefficient representing x cubed, x squared, x, and this was the constant term. After performing synthetic division once, we reduced our coefficients, and they were representing x squared, x, and this was the constant term, the number. So after that, the coefficients that we obtained, the 1 was representing x, and the -2 is representing the constant term. So now we could do the following. We have verified already x equals -3 is a 0. We also verified that x is equal to -1 is a 0. Now if I want to go back to find the factors, this will be x plus 3. The other one will be x plus 1. And now from here, I'm going to take the third factor, and that factor is going to be x minus 2. So if I know the factor, I should know the 0, and that 0 is going to be x is equals to 2, and that proves that our educated guess, x equals to 2, is in fact a 0. So we have found the 3 zeros, and all 3 of them are real. If you recall from looking at the graph, they were touching the x-intercept, and they're also rational zeros. So now let's go to the next example. Here we're going to do the same thing. We're going to find all the zeros for that polynomial. So we start again. We cannot factor this polynomial. So we start by using the rational zero theorem. So we have to list the factors of the constant term, which is -3, and divide them by the factors of the leading coefficient, which is +1. Factors of -3 is positive -1, positive -3. Factors of 1, positive and -1. So now I'm going to list the possible rational zeros. And those will be positive and -1 and positive -3. So what we're going to do now is graph it so that we can make an educated guess. So I'm going to delete this graph. Remember, you can press the delete button and hold it until, well, it's not working. So I guess I can go to menu, actions, and then delete all. and then to enter a graph, press tab. And so I'm going to enter the polynomial on example 4, and that is x to the third power plus 7x squared. Oops, I made a mistake. Oh, sorry, didn't mean to do that. So I'm going to go back and correct it. I'm missing plus 11x, and then the constant term minus 3. So now we can see the polynomial here. We'll move the equation out of the way. Now, if we look at the possible rational zeros that we had, we only have integers. But if we look at the graph, the only integer that we can see here clearly is negative 3. So that is going to be our only educated guess. Now, for the other two zeros, I know that they are real, the one that crosses here and here, but they are not integers, so it's pretty difficult for me to guess what they are. But let's see what we could do after using our educated guess of x is equal to negative 3. So we're going to test with synthetic division using negative 3. And the coefficients are 1, 7, 11, and negative 3. So we need to divide, drop the first term, then multiply negative 3 times 1, that is negative 3. 7 minus 3 is 4, and then we multiply negative 3 times 4, which is negative 12. 11 minus 12 is negative 1, and then we multiply negative 3 times negative 1, and that is positive 3. And then we combine like terms, so negative 3 plus 3 is 0. So the fact that the remainder is equal to 0, that tells me that my first 0 is going to be negative 3. Now, remember when we use synthetic division, we're using only the coefficients, but we know that the coefficients represent variables. Number 1 represents x to the third power, 7 represents x squared, 11 represents x, and negative 3 is the constant term. After performing synthetic division once, we reduce our variables, or the degree of our polynomial, by 1. So this will be x squared, this will be x, and this is going to be the constant term. So now we could try to factor a polynomial of that form. Let's call it g of x. So let's see, we have x is x squared plus 4x minus 1. And so actually I don't need to assign a number to it. We could just equal it to 0 because we're trying to factor. So if we try to factor this one, then we will get x and x. We know the sign is negative, so we have one of each here. The only factors of 1 are 1 and 1. And if you multiply the outer terms and the inner terms, you're not going to get positive 4x. So what that tells me is that that polynomial is not factorable. So what we're going to have to do is rely on the quadratic formula. So remember, well, I'm going to go ahead and write the polynomial we have here. So it is x squared plus 4x minus 1. And I want us to list the coefficients, and we're going to use a is equal to 1, b is equal to positive 4, and c is equal to negative 1. Remember, a is the coefficient of the square term, 4 is the coefficient of a is the coefficient of x squared, b is the coefficient of the x term, which happens to be a 4, and c is the constant term, which is a negative 1. Now we're going to use quadratic formula, so that is negative b plus minus the square root of b squared minus 4ac. Everything is divided by 2a. So what I'm going to do here is substitute those numbers that I have listed here into the quadratic formula. So we're going to substitute b here and here, also a inside the radicand and also a as part of the denominator. So by doing that, we're going to have negative 4 plus minus the square root of 4 squared minus 4 times 1 times negative 1. All of that is divided by 2 times a, so it will be 2 times 1. Now here we are going to have to simplify it a little bit. So we're going to have negative 4 plus minus, well actually I'm going to use the next row. Negative 4 plus minus, we square this part here, so that will be 16. And then if we multiply negative 4 times 1, that will be negative 4. But then negative 4 times negative 1, it turns into positive 4. All of that divided by 2 times 1, which is equal to 2. Now we're going to add the two numbers inside of radicand, so we have negative 4 plus minus square root of 20. All of that divided by 2. Then we have negative 4 plus minus the square root of 20 does not have an exact solution. However, we can find two factors of 20 where one of them is a perfect square. And so I'm going to choose 4 times 5 because 4 has an exact root. Now we keep simplifying and we'll get negative 4 plus minus the square root of 4 is 2, so we take that outside the radicand, the radical, and then the 5 is going to stay inside. All of that is divided by 2. Now keep in mind here that the 2 is dividing the negative 4, so I'm going to split the fraction, and the 2 is also dividing the 2 times the square root of 5. Now what we're going to do next is reduce, and we know that negative 4 divided by 2 is negative 2, and 2 divided by 2 is equal to 1, so you may say they cancel. Now here we have actually two zeros. One of them will be x is equal to negative 2 plus the square root of 5. And the other one is x is equal to negative 2 minus the square root of 5. So I'm going to go back to the top and list them here. X is equal to negative 2 plus the square root of 5, and the other one is x is equal to negative 2 minus the square root of 5. Now, what we can say about the zeros is that the first one, it is real. It touches the x-intercept. We know negative 3 is a real number, and it is also rational. Now, the second and third, they are real, but they are irrational. And one thing to consider here is that irrational zeros, as well as imaginary, they always come in pairs. Remember how we have here positive and negative, so that's where you get the 2 from. Okay, so we're going to go back. We're going to go, not back, but we're going to go to the next slide. And that will be the last problem for this video, part 1. So again, we need to solve the polynomial. Remember, that means to find the zeros. And so again, I can tell you that you are not able to factor it. So what we're going to do is rely on the rational zero theorem again. So we need to list the factors of 24 and divide them by the factors of 1. Factors of 24, we have plus minus 1, plus minus 2, plus minus 3, plus minus 4, plus minus 6, plus minus 8, plus minus 12, and plus minus 24. All of those numbers divided by the factors of 1, which are just positive and negative 1. So when we list our possibilities, possible rational zeros, we could have positive and negative 1, positive negative 2, positive negative 3, positive negative 4, positive negative 6, positive negative 8, positive negative 12, and positive negative 24. So here we actually have a total of 1, 2, 3, 4, 5, 6, 7, 8, but we have to consider positive and negatives. So we have a total of 16 different possibilities. So it wouldn't be fair for me to ask you to test all those 16 numbers. So of course you could use your graphing calculator for a good purpose. And so we're going to go ahead and graph that polynomial. So I'm going to clear my screen first. And I'm going to enter that polynomial. And so it is x to the fourth power minus 6x squared minus 8x plus 24. And then so here's our graph, and you can't really get a good picture from it, so I'm going to do something called zoom fit. So you go to menu, window zoom, and then we will select option A. And so that is the polynomial. Now that is a little useless to me right now because I'm trying to find rational zeros. So I'm going to go back to the standard view. So menu, window zoom, and then standard view, which is number 5. Now what I can see here is that number 2, x equals 2, it is a rational zero. I could see that clearly. However, the degree of this polynomial is 4. So we know that we can have 4 zeros. We do have 4 zeros. But one thing that I noticed is that the graph is touching the x-axis and then it's turning around. And so that reminds me of something called multiplicity. So in fact, that happens when a zero is of even multiplicity. So what I'm going to see is that if it's true that the zero occurs 2 times or maybe 4 times. So let's see. So our educated guess was x is equal to 2, positive 2. So we're going to do synthetic division with positive 2. Our coefficients, we make sure they are in order, but I noticed that there is no x cubed. So remember, when you do synthetic division, you must account for that space with a 0. So for x to the 4th, the coefficient is a 1. For x cubed, the coefficient is a 0. For x squared, the coefficient is a negative 6, and then negative 8, and 24. So we do synthetic division here. And now we drop the first number is a 1, then we multiply 2 times 1 is a 2, 0 plus 2 is 2, 2 times 2 is 4, negative 6 plus 4 is negative 2, 2 times negative 2 is negative 4. Negative 8 minus 4 is negative 12. 2 times negative 12 is negative 24. And if we combine like terms, 24 minus 24 is 0. So I have verified that x is equal to 2 is a 0. Now let's see, well, we know it's even multiplicity, so let's check if it is actually happening twice. So remember, if you get a remainder of 0, you have proven that not only x equals to 2 is a 0, but also you know that the factor is x minus 2. Now, it's not necessary to go back to the original coefficients, but we could use the new coefficients that came after performance in direct division once. So now we drop the first number as a 1, and then we multiply 2 times 1 is 2. 2 plus 2 is 4. 2 times 4 is 6. Negative 2 plus 6 is 4. And then we multiply. So I made a mistake here. So let's just go back. So we drop the first number, and then 2 times 1 is 2. Combine like terms, 2 plus 2 is 4. And then 2 times 4 is 8. I had initially written 6. That was a big mistake. It should not be 6, it is 8. Then negative 2 plus 8 is 6. And then 2 times 6 is positive 12. So now negative 12 plus 12 is 0. So now what I have proven is that x equals to 2 is a 0. So we may call it a 0 of even multiplicity. Even multiplicity, and that's why the behavior of the graph around the x-axis was touching and turning around at x is equals 2. Now let's go back and trace our steps. So we started with a polynomial of degree 4. And then after performance of direct division once, we got x to the third power. And after that, we got something x squared. Now here, what we could do is consider a polynomial of second degree. Let's call it g of x. And so that will be x squared plus 4x plus 6. And I can tell you right now that there is no way you could factor this. So again, we're going to have to use quadratic formula. So remember, a is the coefficient for x squared, that's 1. B is the coefficient for x, that's 4. And c is the constant term, which is positive 6. So now I'm going to use the quadratic formula, and that will be negative b plus minus the square root of b squared minus 4ac, everything divided by 2a. Negative b will be negative 4 plus minus the square root of 4 squared minus 4 times 1 times 6. So what I'm doing is substituting a, b, and c. Now we're going to simplify that expression, and we get negative 4 plus minus 16 minus 24, everything divided by 2. What we have here is negative 4 plus minus 16 minus 24, that is actually equal to negative 8. And so we know now that there is no real solution to that because we have a negative inside a radical, inside an even root. So what we're going to have to do, we could imagine now that we're going to have some imaginary numbers for our solutions. So what I need to do is factor negative 8, and I'm going to use negative 1 times 4 times 2. And so we all know that the square root of negative 1 is, well, let me go from the left. So negative 4 plus minus. Now we take the square root of negative 1, and that is equal to I. The square root of 4 is 2, so we take that out of the radical. And then the square root of 2, that is an irrational number. It does not have an exact solution, so we leave that 2 inside. Everything here is being divided by 2. So now what I'm going to do is simplify the fraction. So we have -4 divided by 2 and plus minus 2i square root of 2 over 2. Now here we know that -4 divided by 2 is equal to -2. And here we're only going to divide 2 over 2, and that is equal to 1. So 1 times I square root of 2. Now that 1 is not really necessary. I could simply write -2 plus minus I square root of 2. But remember, from here, we're actually getting 2 zeros. One will be x is equal to -2 plus I square root of 2. And the other one is x is equal to -2 minus I square root of 2. And one interesting fact about both of the zeros is that they are complex conjugates. So anytime you have an imaginary zero, you're going to have its complex conjugate. So they always come in pairs. Just like not rational, but irrational zeros do. And so this is the end of video of section 2.5, part 1. Part 2 is also uploaded on YouTube.